All right, so let us start. It's my pleasure to introduce the second speaker today. Of course, he doesn't need any introduction here in Granada, at least. He's, well, let me say, he's one of the pillars of this geometric school in Granada, together with Antonio, and also I should mention Sebastián Montiel. And of course, he was a professor of mine for a long period. And now I'm very happy to, of course, I have to say that we are all very thankful to Francis because he agreed to give this 8-hour course, which is a lot. And partly, I want to recognize his effort. He's currently retired, but I know he's very active, still very active, and I want to somehow to push him to keep this activity, okay? So it's again my pleasure to give the floor to Francis. Thank you.
Good morning. Well, the first thing that I would like to say is to give my thanks to the organizer, and in particular to Joaquin, for giving me the opportunity to talk here about this interesting topic. As I suppose you have noticed, my level of English is quite regular. Okay? I apologize for that, but anyway, I hope that you can follow the course without it. Okay? Well, you have some notes that I have prepared for you. In this note, I have there is a short introduction to the topic. Appear all the references that I have used in the course, and also some definition and technical lemmas that will help to follow the course. Okay. Anyway, at the end of the conference, the presentation, I will put the presentation on the web page of the institute, so no worries. Okay.
Well, yes, sorry for the interruption. About the notes. For those of you that do not have the notes, students, they have the notes, but there you can see in the corner of the room, there are some copies of the notes. Okay.
When the organizer contacted with me in order to give this course, they proposed a very general, typical topic in Granada, minimal surface or minimal submenu. But it's a very, very wide topic. And then I choose this subject mainly because it's a current topic. Okay? Because during the last 3 years, very young mathematicians from different countries, the United States and France, have developed this theory in a very nice way. Even the last month, appeared a paper of Laurent Masset, this one, in which he has a very nice contribution to this topic. Okay. Well, the minimal hypersurfaces of the minimal submanifold in general appear as critical point for the volume function. Okay, so they are critical point for some. They are solution of some variational problem, and in geometry it's natural that in that situation you study the second variation in order to study when this in order to study the stability of the critical point. Okay, this is natural in any situation, and in particular in this one. Well, so we are going to study this problem in a family of submanifold very simple, the beginning, because the problem is very, very hard, which the ambient space would be the Euclidean space, everybody knows very well its geometry, and the hypersurface will be always orientable, okay, because in the non-orientable case, there are only few results, very few results. Well, let me explain a little bit the history of this problem. Okay, in my opinion, the first result is just the result that has been proved in the last talk. Okay, the bursting problem or the bursting theorem is a theorem that was proved by Bernstein at the beginning of the 19th century, in which he proved that the plane are the only entire minimal graph of the Euclidean space. Okay? Then, in that time, I suppose that the point of view of that time was not the minimal graph, because probably he was interested in studying solution of this equation defined on the whole plane. This is equivalent to have an entire minimal graph, okay, but probably in that time, the analytical point of view of the problem was most interesting. He proposed a problem, which is the classical Bernstein problem, which is what happened in higher dimension. It's true that for the hyperplane are the only entire minimal graph in the Euclidean space of dimension n+1, with n bigger than 2. Well, this problem was solved 40 years later, okay, in the 60s. Then in the 60s, many important mathematicians, like that guy Fleming, Algren, Bombieri, De Giorgi, Giusti, and James Simon, from 62 to 69, solved completely the bursting problem. Okay? In which way? They proved that for n less than or equal to 7, the only solution are hyperplane. And for n equal to 8 or higher, there are solutions which are not hyperplane. Okay? During the preparation of this course, I have read a paper in which the authors say that Gilbert, the author of the famous book of Gilbert Trudinger, was in the 60s in California. And he said, I am astonished how it's possible that the same equation have only trivial solution until some dimension, and for higher dimension there are non-trivial solutions. And he said, it's the magic of the geometry. No? He said in that time. Okay. So they solved this bursting problem. Bombieri, De Giorgi, Giusti constructed a sample in dimension 8 for n equal to 8. Algren proved the result for n equal to 4, Giusti for n equal to 3, and James Simon for n equal to 5, 6, and 7. Okay? I'm not going to prove the original result. I will prove another result that you can prove using different technique. Well, 10 years later, at the end of the 70s and the beginning of the 80s, the bursting problem was generalized in the following sense. This mathematician proved that the plane are the only orientable, complete, stable minimal surfaces of R3. I am saying that this is a generalization of the bursting problem because an entire graph is a complete surface. And any minimal graph is stable. Okay? And the graphs are orientable, of course. So this is a generalization of the bursting result. And there are 3 different approaches to the proof of the result. The first one was given by Do Carmo and Penn. This is a demonstration which is that is typical for surfaces. They use that the surface is a Riemann surface. They use theory of Riemann surface. So it's not, you cannot use this idea to pass to higher dimension. The paper of Pogorelov was written in Russian, and in my opinion, is important because now the last theorem have used some more or less his ideas. Okay, he proved the result, seeing that the surface has Euclidean volume growth. Okay, the volume of the ball grow like in the Euclidean space, in the plane. And finally, Fischer-Covey and Schoen proved the result as a corollary of a more general theory, because they studied not only the Rodinger operator which appear here, they studied any Rodinger operator, and their paper has been quite important in many different situations. Okay. Anyway, I will prove in this course the Docarmo pen like a tribute to him. Okay. Well, so it's natural to consider the following problem. Young people now, Chodos and his collaborator call to this problem the stable Bernstein problem. Okay. It's nice. And then what happened here? The stable Bernstein problem say, are the hyperplane the only orientable complete stable minima hypersurfaces in Rn+1? This is the generalization to higher dimension of the theory, of the last theory. Of course, a partial solution is no, because you have the graph. And then this problem was has been completely solved in the last 3 years. Except the paper of Bombieri, the Giorgi Giusti, where they found a 7-dimensional stable complete minimal hypersurfaces of the Euclidean space of dimension 8. Okay? And the other mathematician proved the result. For instance, Chodor and Lee, they gave 2 different proofs for the case n equal to 3. The first one, in my opinion, is very complicated. I have read the paper, but it's very complicated. And even they have used the second idea in order to generalize for higher dimension. In the same time, Catino, Mastrolia, and Roncoroni gave another different proof for the case n equal to 3, using the ideas of Fischer-Covey and Schoen. In this course, we will prove this approach. And finally, in this year, in January and in May, then it's difficult to prepare a course in which every day appears a new paper. No? Then Chodos, Lee, Minter, I don't know if Minter is to pronounce, and Stryker proved the result for n equal to 4. And in the last month, Laurent Masset proved the result for n equal to 5. In fact, on Friday, he will talk about this result. It's important, no, to follow the course. Then the last idea that people have used is a new technique, at least for me, but probably you will know the technique very well, which is the mu bubbles, or the mu bubble. It's a technique introduced by Gromov, okay, and they have adapted that technique in order to incorporate that technique in the study of the hyperstability. So very nice. So the only problem, the only open problem is for n equal to 6. Okay. So, because to classify the stable is impossible. There are many samples in higher dimensions. Okay. I don't know. Probably today is appeared. I don't know. Okay. Well, then we are going to start with the first definition, and the notation that I am going to use. Then suppose that Rn plus 1, the bracket will be always the Euclidean metric. Then a hypersurface as an immersion of an n-dimensional manifold there. And I will assume along all the course that the hypersurface is oriented. Okay? Because in the non-orientable case, there are not many reasons. So I will denote by G the induced metric in the hypersurface by the Euclidean metric. And for N, the Gauss map that, as everybody knows, is to take in each point a normal vector perpendicular to the tangent. And as the manifold N is orientable, the Gauss map is globally defined. Okay? In the non-orientable case, you don't have a globally defined Gauss map, but in this case, yes. Now, if you take the Gauss map, you can consider its derivative. This means the shape operator of the second fundamental form of the hypersurface, and then I will call A, and up to the sign is simply to take the derivative here, to take the derivative here, and to use this isomorphism to go to define an endomorphism on the tangent space. This endomorphism is a Lagrangian, as everybody knows. You can diagonalize it. The principal curvature appear, but for us, it's important to consider the trace of the second fundamental form up to a constant. The trace of the second fundamental form is the mean curvature. Okay, and our hypersurfing will become minimal if H is values. Okay. Well, now let me explain, only to remember this property. If you take the Laplacian of the induced metric on the manifold N, and you take the position vector of the hypersurface, is defined n plus 1, you take its coordinates, phi 1, phi n plus 1. Then the Laplacian of the position vector is very easy to prove. That is exactly n times the mean curvature times the Gauss map. So if the hypersurface is minimal, all the functions phi I are harmonic. And in a compact manifold, the harmonic maps are constant. So if the immersion is minimal, n is necessarily non-compact. This is important. Okay? This is important to know. Well, now, in the case in which the hypersurface is minimal, the curvature of the hypersurface can be written in terms of the metric and the second fundamental form, which is very well known. But the important thing here is that the Ricci tensor of applied to two vectors B and W is given by this way, and so the Ricci curvature is non-positive. This is quite important. So we have any hypersurface non-compact and with non-positive Ricci curvature. Okay, and in particular, the scalar curvature rho is always non-negative. Okay, I don't know, but I believe that I will use the last equation here in the Kodashi equation, in which if you define the covariant derivative of the second fundamental form in this way, okay, then this two tensor is symmetric. The property, technical property was interesting. Well, let's go with the sample. First sample. I suppose that everybody knows that. If somebody doesn't know the result, you can do this if it's not easy exercise, no? Which is that in the case of the hypersurface, the totally geodesic hypersurfaces, this means that the hypersurfaces that have the second fundamental, in which the second fundamental form vanishes, are the hyperplane or they are open subset. Okay, this is very well known. These are the first example, the hyperplane. How are we going to study the next example? Using graph. Okay, so let me introduce the notation. Although suppose that I take a open domain into the Euclidean space omega and as an infinity function. I don't need to be say infinity. I assume the infinity of with the function is smooth. I only need to be of of C2 omega. Okay, then I can associate to this function a graph, which is a hypersurface, which is embedded. Embedded means that the map phi is 1 to 1, defined in this way. I decompose the Euclidean space as a product, then for any point x into omega, which is a point of Rn, I take this image. Okay, so it's very easy to prove that the induced metric on omega is given by the sum of the Euclidean metric in Rn plus these two tensors, which is the differential of f times differential of f. Okay, this is the induced metric. And the Gauss map, which is globally defined because omega is orientable, the Gauss map is minus gradient of f here, Rn, 1 in this another factor over the square root of this one. Of course, this gradient is computed with respect to the metric, with the Euclidean metric. Okay, and then using that n is given by this one, it's very easy to take the derivative here and to compute the mean curvature. And the mean curvature has to a constant is the divergence of this vector field into omega. This is a vector field on omega, and the divergence is computed with respect to the Euclidean metric. Okay, this is very well known. So a graph phi is minimal if and only if the function f is a solution of this second order differential equation in here. Okay, when I consider functions which are polynomial of degree 1, this means I take a vector in Rn and a real number b, and I define in all Rn this function, then this is a trivial solution of this equation. The corresponding graph is the hypersurface. Okay? Well, this is important to remember this equation. And now let's go to study the relationship between the minimality and the volume function. Okay, it's also very easy. You take an hypersurface phi, then you compactly supported variation is a family or is a smooth map f defined on the cylinder over M. We satisfy the following condition. For t equal to 0, we recuperated the immersion phi. At any t, phi t is an immersion, or the variation is by an immersion. And the last one is that the variational vector field, which is nothing but the derivative of f with respect to t at t equal to 0, which is a map from n into Rn plus 1 has compass points. Okay? So it's like before, you take, I'm going to write one-dimensional one, then you are taking a variation. This is the compass outside. You don't move the sun. Okay? So in this situation, we can define the volume of the variation, which is a function defined in this interval, and at any t is the volume of, I have taken some domain omega bigger than the support in order to work better. Okay? Of course, some people can say then the volume depends on omega and the variation, yes, but the derivative, no. Okay, so it's better here. So, and then you take the induced metric by the immersion phi t, gt, and integrate the function 1 with respect to the canonical measure here and compute the volume. Okay, then you have the volume of the variation. Well, the first variation formula is this one. If you take the derivative of the volume with respect to t and t equal to 0, you get up to a constant the integral over m of h, the mean curvature, times the normal component of the variational vector field. Okay, the variational vector field can have tangential component, but it doesn't appear in the data. Okay, so as a consequence, we have that the immersion of the hypersurface is minimal if and only if it's a critical point of the volume function. If h is equal to 0, if h is equal to 0, then this derivative vanishes for any f. And conversely, if this vanishes for any variation, you take here, this is a function with compass support, and then h is L2 orthogonal to any function with compass support automatically. H vanishes, okay? Without problem. Well, in this situation, for critical point, if phi is a minimal hypersurface, the second variation formula is given by this one. Again, appear only the normal component of the variational vector field, and here appear the energy of the function f, and here the length of the second fundamental of the hypersurface. Using integrated by parts here, or using the divergent theory, the same, the energy can be changed by this one minus the integral of f Laplacian of f. Okay? Well, I'm not going to prove this formula, but I suppose that perhaps some of you never have proved the result. Then let me give some idea if you want to prove the two formulas that I have written there. Okay, I take a variational vector field x, and f is a infinity function with compass support on the hypersurface. Okay. Then I'm going to construct the following variation. Phi t is phi plus t f n. Okay? This is for t small enough, phi t is an immersion, and this is a variation of our hypersurface phi. Okay? So now, if you take the derivative here, the differential of phi t over any vector t is equal to the differential of phi over v plus t gradient of f v n minus tf, the second fundamental form applied. Okay? So the induced metric gt is equal to this one g. This one is tangent, this is normal, doesn't appear. This tangent, this is normal, doesn't appear. Then appears this one with this one is minus twice t f g a applied to the two vectors which appear here, plus t squared. Here appear the gradient of f times the gradient of f, because n is unit, plus f squared g a. Okay. So the dependence of g with respect to t is very simple. It's a polynomial of second degree. Okay. And now, in order to compute the volume, right here, you only use the identity here, and use the variable chain formula. Okay. So the integral over n of g t here is equal to the integral over n of dv, and here appears the Jacobian of the identity, which is the square root of the determinant of gt. Okay? So now it's very easy to perform, because you only have to take the derivative of I square root the determinant, and here you have the metric, very simple. Okay? Of course, not all the variations are of this type, but it's enough to consider only this variation. Okay? Maybe a good exercise if somebody doesn't know well this one. Well, in this situation, a minimal hypersurface is called stable if the second variation is non-negative for any variation f of the inverse. Okay? So the stability is equivalent to this inequality. This is the classical stability inequality, in which the energy of any function with compass support is bigger than or equal to the integral over n of h squared f squared. This is the only thing that we have. Okay. From here, we have to produce many problems. But the only thing that we know is that. Well, here, let me say a little bit something. In the notes, I have introduced the Sobolev space that everybody also knows. Then, if I consider the Sobolev space H12 of n, the space of function with weak derivative, okay, then the function, this infinity function with compass support is included here. Okay, and then I can take the closure of this one in this space, and this is called H1 to 0 of n. Okay, then as this operator, these two operators are continuous with respect to the topology here, this inequality can be extended to this space. I will use this one along the course many times. Okay? Well, here in the second expression, the second derivative appear as Schrödinger operator that I have called L, which is the Laplacian plus a potential, and the potential of the Schrödinger operator is the square of the length of the second fundamental form. This is called the Jacobi operator of the hypersurface. Okay? Well. Now, I'm going to start with a characterization of the stability. For that characterization, I don't need any global assumption about the hypersurface. I don't need a complete nothing. And this characterization is quite important because it has many consequences. And during this year, many people have used this characterization. This characterization was given by Fisher, Cobry, and Schoen in the 80s, 1980, and in our case, say that if I take a minimal hypersurface orientable in the Euclidean space, then this hypersurface is stable if and only if you can find a positive function in the kernel of the Jacobi operator. If you want the function in the kernel of the Jacobi operator are called Jacobi function, then the stability is equivalent to find positive Jacobi function defined on the domain. Okay? Well, they prove the result not in this situation. They prove the result in a more general situation, and we are going to prove the result in that more general situation. Okay? Well, before to prove the theorem, let me give two corollary quite interesting for the development of this topic. The first one is the following. Suppose that I take an orientable, stable, minimal hypersurface in the Euclidean space. Okay? And now I take a covering of the manifold N, any covering. Then you have the corresponding composition of the projection of the covering with the original immersion. And then this new map is also an stable, orientable, minimal hypersurface. It's quite important to say that this is not true in general. What does it mean? If instead of to have the Euclidean space as an ambient space, you have another kind of Riemannian manifold, this result is not true. For instance, in the sphere compass submanifold, minimal compass submanifold are not stable, but they have index. Then generally, you take any stable minimal submanifold in certain manifold, the covering are not stable. But in this case, yes. Why this is important, the result? Because if you try to classify the stable minimal hypersurface of the Euclidean space, you can consider the universal cover of the manifold. And so you can assume that your hypersurface is simply connected. Okay? This is important. If you classify the simply connected, later on you will classify the quotient. You can reduce the problem with this situation. Okay? How to prove this one? Well, it is not difficult because the situation is this. You have the cover N, phi, Euclidean space. Here, the composition, phi theta. So pi is a local diffeomorphism. Okay. It's a local diffeomorphism. So here you have the metric G, the induced metric, and here you have the induced metric G tilde. Okay? And this metric is the lift of G to the cone. So, with respect to this metric, pi is a local isometry. Okay? It's a local isometry. So, it's simple that this is a hypersurface. It's orientable because the covering of any orientable manifold is an orientable manifold. And minima. Why? Because if you take the mean curvature of phi and you compose with pi, this is the mean curvature of phi theta. It's very simple. Okay? Because pi is a local isometry. Locally is isometry. So if H vanishes, H tilde also vanishes. So the lift, the phi tilde is minimum. And now what's happening with the stability? Then we are going to use the theorem. Okay? Because if phi is stable, there exists a positive function on M such that the Jacobi operator is equal to 0. Okay? There is a Jacobi function on the manifold N which is positive. And now I consider U tilde is equal to U proposed with the projection. Okay? And then it's easy to see that L tilde, U tilde is equal to LU proposed. Because the second fundamental form project in each other is very simple. So U tilde is positive, and this one vanishes, then you see the result of the cover. Okay? when we prove the result, we will see that the no compacity is crucial. Okay? Well, this is the first corollary. So in order to classify, we can assume simply connected on the main. The second corollary is to prove that the minimal graphs are stable. Why? Any minimal graph into the Euclidean space is stable. Well, very simple. You take for any minimal hypersurface, you take the function given by the inner product in the Euclidean space of the normal vector field times any fixed vector of the Euclidean space. Okay? And then you compute the Laplacian of the one. Okay? I take an orthonormal basis on the manifold, then EI, the derivative of M with respect to EI is equal to minus A EI A. So this is constant here. And now the Laplacian, the second derivative of the function f, is equal to minus the derivative of A applied to EI plus minus, sorry, now the second fundamental form. But this one vanishes because it's minimal. And this one is the length of the second fundamental form. So this is equal to minus A squared. Okay? This is very simple. What does it mean? It means that L of F is equal to 0. This is more general because a vector field into the Euclidean space is a Killing vector field. And so the restriction of a Killing vector field to the surface, if you make the inner product with the normal vector field, is always a Jacobi function. Okay? So this is true for any minimal hypersurface. What happened with the graph? With the graph happened the following. If you take the function which define the graph, okay, the normal vector field is given by minus the gradient of f1 over the square root of 1 plus gradient of f squared. Okay? And now I can choose any a in the Euclidean space. Then I took a equal to 0, 1. 0 is a vector in Rn. This is the origin of Rn, and 1 is a real number. Then the product of n a is 1 over square root 1 plus gradient of f squared. Okay? But this function is positive. So we have found a positive function in the kernel of the Jacobi operator. What does it mean? It means that the graph, a minimal graph, is automatically stable. Okay? It's very simple, but it's important to say. Well, now let's go to prove the theorem. Okay? As I mentioned before, I am going to write I am going to prove the result in a more general context. Suppose that I have a Riemannian manifold without any this abstract Riemannian manifold M, and I consider a Schrödinger operator given by Laplacian plus certain function Q with the typical property that you assume on this kind of theory. So this operator is stable. I will say what stable means if and only if there exists a positive function in the kernel of it. Okay? But it is important to say that the manifold is non-compact. Why? If you assume that there exists a positive function in the kernel, automatically the hypersurface is stable. L is stable. Even in the compact case. But if you assume that L is stable and the manifold is compact, you cannot find this function. Okay? Why? Let me explain. It's very simple, but it's important to see why this is true. So the situation is, I take a compact one, a compact Riemannian manifold, and suppose I have to prove that L is stable doesn't imply this assumption. Then I define L like Laplacian minus 1. The potential function for the Schrödinger operator is constant, minus 1. Okay? So, let me see. If there exists a positive function in the kernel, we have a positive function satisfy this equation. Okay? But this equation, what does it mean? That minus 1 is an eigenvalue of the Laplacian. And in compact manifold, the first eigenvalue is C. Okay? So it doesn't true the theorem in the non-compact case. Okay? In the compact case, sorry. Well, now let me explain first this sufficient condition. The sufficient condition is not complicated. Well, we have that there exists a positive function such that Laplacian of u plus qu is equal to z. Okay? And I want to prove that the operator L is stable. So I take w equal to the logarithm of u. And I make computation here. Then the Laplacian of w is equal to the Laplacian of u over u minus the gradient of u squared over u squared. We're taking the second derivative of the logarithm. But Laplacian of u over u is positive, I can divide by this, is minus q. Okay? This is what? Minus q. And here, the gradient of w is equal to the gradient of u over u. So this one is minus the gradient of w squared. Okay? Then, now I take any function in compact support on the manifold, and I compute the integral of q plus gradient of w squared f squared. I'm going to compute this one. Okay. Then this function is equal to minus the Laplacian. This is 1 minus the integral of the Laplacian of w times f squared. Okay. And I wrote this one in the following way: minus the integral of the divergence of f squared gradient of W minus twice F G gradient of F gradient of W. Okay? Here the divergence is equal to F squared, the Laplacian, which is written here, plus the gradient derivative, the derivative of F squared with respect to the gradient, which is the divergence theorem vanishes this one because F is of common support. And now here I use the sparring inequality, minus minus plus, and this is less than or equal to. By sparring inequality, integral over n, and I put this one in this way, F squared gradient of W squared plus gradient of F squared. Okay. What are we doing? One here, this one here, and minus, which is plus. Okay. And now I simplify. Not the same. We obtain that the energy of the function f is bigger than or equal to the integral of q squared, which is means that the L is certain. Okay? So it's very simple. Very simple. The proof is only to consider the positive function, the logarithm, and to make a very easy computation in order to get that the operator is stable. What?
You need Q positive.
Q?
Your Q must be positive.
U.
Q.
No, no need for any operator. No.
Ah, because if it's negative, it's completely, then it will not. It never occurs. In fact, it never occurs.
This happens in manifold
Automatically.
when you study stability in manifold with negative coverage.
Yes.
They use up to be totally geodesic, something like that. They are stable. Okay. Well, now let me explain the more difficult part, which is the other one. Okay? The construction of the function u. I have time.
Well, you have 10 minutes. A bit less, just 8 minutes.
Only.
Yeah. You started at 10 past.
I don't know to prove tomorrow or today. Okay, now we take this. Probably I will prove some part. And tomorrow I will keep 9 minutes, is impossible. Okay, I take this operation in a non-compact. Okay? And I assume that for any function to come to support, we have this inequality. The energy is bigger than or equal to. This means that the operator, the Rodinger operator, is stable. Okay. Then I'm going to construct u in which way? I will construct a function u in every domain with relative compact domain. Okay. Well, to follow this proof, you need section what? Section 3 in the notes. Okay, because I am going to use the Frege alternative, I'm going to use the maximum principle, I'm going to use the Harman inequality and so on. Okay? It's not easy to prove. Well, then the first eigenvalue, I take a relatively compact domain manifold, okay? Then the first thing is that the first eigenvalue of this operator, lambda 1 omega, which is defined in the notes, is the infimum of the quotient between over the integral of f squared with f in h1 to 0 of n. This is the definition of the first eigenvalue of a Schrödinger operator with certain domain omega. Okay? Zero.
Omega.
Zero. Okay. So this inequality means that the first eigenvalue is always bigger than or equal to 0. Okay? The first thing that I'm going to prove is that the first eigenvalue is really bigger than 0. It's impossible that the first eigenvalue for some relatively compact domain will be 0. Why? I use the no compacity of the manifold. Okay? Given omega, I take the closure and I can find another domain, relatively compact domain, which includes the closure of omega. This is impossible in a compact manifold. So you can take like omega or the manifold, but in a non-compact, it's possible. Okay, now in here, there are more functions than there. Because with function in the little one, I can construct like function in the smaller space of the biggest one. Then the infimum is small. Okay, so you get that the first eigenvalue of omega prime is less than or equal to the first eigenvalue in omega. And this is 0. I'm assuming. Going to get a contradiction. Okay? But this one is always bigger than or equal to 0. So lambda 1 omega prime is equal to lambda 1 omega equal to 0. For any omega prime, including omega inside. Okay? Well, as I am assuming that the first eigenvalue of omega is 0, there exists a function in omega such that satisfy this condition. Okay? The definition here, because if some function attain in the note appears that the first eigenvalue of a Schrödinger operator, the corresponding eigenspace is one dimension, and you can find positive function in that space. Okay, so you can find a positive function which satisfies this equation because I am assuming that lambda 1 omega vanishes. Now I define u tilde in omega prime this way. U tilde is equal to u in omega 0 omega prime z minus the closure of omega. Okay, and then this function is non-negative and of course satisfying the same one. But in the node, you can find the maximum principle. In fact, the maximum principle is not exactly the maximum principle that I wrote in the paper. It's a consequence of the maximum principle. Then you have a Schrödinger operator and you have a function which is non-positive and is in the kernel of this one, then automatically this function vanishes or is positive. But it's impossible to vanish because is equal to omega is equal to u in omega. So you get a contradiction. Okay? So the first thing that we have proved in this one, here, that for any relative compact open subset of M, the first eigenvalue is positive. And I finish here, and tomorrow we will continue. Okay? Thank you very much. Everything is clever. No, it's clear.
Everything is clear.
Clear.
Nothing was understood.
So, for those of you that have the poster here, please handle the poster to your administration. So she can show you what is happening, okay?
Ahí